Okay, my wonderful students, welcome back to classes. Uh, just to remind you, um, the final exam is mandatory in this class, and you're required to take it. You may not take it at any other time. If you're on the Section 1 roster, you're going to need to be here at 1 o'clock on Saturday, December 10th, in this room. All right, now the other section, they're going to be down the hall, but you guys are going to be in here. And I'm going to go over this as many times as necessary because on exam day, if somebody does come and they don't come to the right place or they come late or they miss it, I'm going to have gone through this so many times that nobody's going to be able to say, oh, I didn't hear the message, Dr. B. So we've got homework 12 ready for you right after class. Let's get to it. First, a few things about exams and so forth. There's a new line in your grades page. You may have noticed it. It's called Participation Pointage Estimate as of October 13th. Now, that was the date of Exam 2. And I still have last week's clicking to update, and I'll try to do that. But as of, for instance, going into the final, you can look at your clicking pointage in the grades page. It looks like this, right on this line down here. And with that, you can figure out your semester grade estimate, you know, what I would do with letter grades. And as a side note, let me draw your attention to this gray rectangle. See that gray rectangle? How do you spell gray anyways? G-R-E-Y or G-R-A-Y? See, because I've always wondered about that. But if you look at that gray rectangle down there, I want you to memorize this concept. No. N-O. Do not pay attention to any of that stuff down in the gray rectangle ever if you want to stay friends with Dr. B, because that stuff and all the other percentages that they put out as purporting to be your grade in this class, ignore it. They have no idea what my grading scheme is. You can't put in a grading scheme like ours into web courses. So what you have to do between now and the final exam is do it yourself. All right? And don't pay attention to that gray rec. Now, if you spell it G-R-E-Y, you have to ignore it. But if you spell it G-R-A-Y, you also have to ignore it. So just ignore it. All right? Now, the participation pointage, as I mentioned before, is based on answered questions. And it's out of 25 possible. And you can estimate your grade. You can estimate your grade estimate. Good. Nice little typo there, Dr. B. As of the 13th, in other words, going into exam 2. There's going to be more updates on that, on the clicking, hopefully by Thursday or Friday, later this week. And just to remind you, we went over this procedure last Thursday. And oh, by the way, the Thursday lecture, for some reason, got discombobulated. I couldn't render it into video and upload it to YouTube. So if you did miss Thursday lecture, last week, lecture 18, you can pretty much get the equivalent lecture from the noon sections, lecture 18, which definitely was recorded. Okay, about the semester grade estimates. A couple other things I want to mention to you, and that is 505 students have got scores on both exams. And for those students, the average is 77%. Now, there's another few dozen students that only have one exam grade. Right? So what I'm saying now, for the next minute or two, doesn't apply to those students, but for most everybody, 505 of you guys, yes. And I want to show you basically how the letter grades stack up. If I were doing semester letter grades, this is what the distribution would look like. Now, I want you to look at it carefully. There's a few. I don't see everybody eyeballing this. You should be taking a look at this. This is how they stack up. There's a few Fs, students below 75 points. There's a few Ds, students below 90 points. There's a few C, or a big pile of Cs, and a really big pile of Bs, and a decent sized pile, 50-something students who, if I were giving letter grades today, would have an A, letter grade A. And you can figure out where you stack into that. Now, that is going by the straight performance criteria that is published in the syllabus. And as you recall from the syllabus and our discussion of it, I do not grade on the curve. All right? If I did grade on the curve, this is what the distribution of grades would look like. All right? This is the curve. All right, now I want you to look at that carefully. All right? We're going to analyze this. So use your powerful mind and visually look for the differences and similarities between the curve and the true grades. All right, look at it. Here's the curve. And here's the true grades. All right? And here they are side by side. All right? Now, I want you to look at that, and I want you to raise your hand and tell me something unusual. Do you see anything strange or something that doesn't seem quite right? In the middle. Can you say it a little louder? Yeah, there's some change. C stayed about the same, but C is very interesting. A's are a little bit higher on the curve. D's are a little bit higher on the curve. What? And F's are a little bit higher on the curve. Now, I looked at this very carefully. So what I did was for every student, all 505 students, I figured out the letter grade that I would give, and then I figured out the curve grade, kind of like how, an SAT score is basically a curve score. It's based on the average. I think the average is supposed to be 500. And so I use the same curve method, although I'm doing letter grades. Now here's one of the first things that I noticed. I don't think you guys mentioned it. Look at that. The curve actually empties out the B's. The B's get shifted down into the C's. A lot of them. 53 students by Dr. B's grade scale had B's. But if I were to curve them, 53 of them would have C's. That's 19% of the B's. Here's another shift that you might want to think about. So your comment that the C's stayed the same, what is your name again? Yo. What is your name again? Yeah. Zach? That's your name? Okay, Zach. You pointed out the B's, and what happened was the C's got emptied out and filled back in. A lot of students that had B's got C's. A lot of students that had C's became D's. Now look at the numbers of this. In the Dr. B grade scale, 56 students had C's, but they got pushed down by the curve into the D's. And that is why, even though B's got shifted into C's, some of the C's got shifted into D's. And so the curves, now here's the really bad one. This little old parcel of students down here, see if I got my cursor. Where's my cursor? Here we go. This little parcel of D's down here, they got shifted too. A bunch of them into the F's. So they had a passing grade. I guess D is considered passing. It's not failing. And a lot of them got cut down to F's. And look at how many of these. 67%. Question in the back. That's not a true curve. A true shifting people always to the left or to the right, it doesn't always work that way. What I'm explaining to you is the fact that forcing this distribution of grades or this distribution of performance, the number of points, into a curve is unjust. And it rips off an enormous number, over 100 students. So what is that, 50, 109 plus 12, 121 students. That's like a fifth of the class. 20% of the class get ripped off. That's no good. And so when you see me say on the syllabus that I do not grade on the curve, that is why. So we're never going to have this. This is the grade distribution that we're going to stick to. All right? And another way that I describe this is if you earn an A, Kristen, you get an A. If you earn a C, I'm not going to take it away and turn it into a D just because of the curve. Forget about that. My whole thing is to break the curve. I want you guys to break the curve into smithereens. And you guys are doing that. We got a lot of you guys doing good. That is what boy, I'm starting to get excited. My job as a teacher is to help you guys bust the curve. All right? And many of you are doing a nice job of that. All right? Questions? One or two more questions. All right, let's keep going. You know, me pounding on the table, I think that's going to come through on the podcast. Nice. All right, let's get back to waves. We started out with this, and what I want to do actually up here is a demonstration with Darian, and I need one student. Come on up. No, wait a minute. You've already done demonstrations. Kristen, do you want to come up? All right. Now, what I want you to do is, can you take the lid off, please? And we're going to do the coil springs. We did this on the first day, didn't we? This resonance, we did do that? All right. So, Okay, now, Darian, move this way a little bit so that everybody over here can see. All right, you guys over here watching? We're doing a demonstration. Let me turn the lights on. Don't slack off on me over here. All right. Now, what Darian is going to do is start oscillating. That's just. Wait a minute, let me see this. The waves go up. Wait a minute, stand back here. The waves go from me towards Kristen. See that? And then they ricochet off Kristen. She's holding it nice and tight and come back towards me. So it's almost like Kristen is a second. Go ahead and make a note. Kristen is like a secondary source of waves. Because the waves that come into her reflect back out just as if she'd been the one shaking. Now, do it again. Now, you don't see anything moving from left to right or from right to left. The waves actually are, but they have the appearance of just oscillating up and down. This is called a standing wave. Back towards the wall so everybody can see. Go ahead and make a sketch of this. The waves are traveling left and right, but they have the appearance of they're not really moving, they're just going up and down. They seem to be standing in one spot. This is called a standing wave, and my wonderful students, make a sketch of a bump and a dip. It oscillates between the bump and the dip. And at a certain rate, a certain frequency. This one is known as the fundamental mode. So write that down as a vocabulary term, the fundamental mode. And I'm going to give you a clicker question about it in a minute. Now, this is not the only standing wave that Darian can create. Go ahead and get this first excited state. And she's got to do this at the right frequency. There we go. All right. Now, this mode, she's wiggling it at a higher frequency. Right? So make a note. This is called the first excited state. Whoops. And not all frequencies work. You got to get it just at the right. There it is. Now this one has a bump followed by a dip, and then oscillates between a bump followed by a dip and a dip followed by a bump. So go ahead and make a dip and a bump, and then in a dotted line, a bump and a dip. All right, in your notes. All right. This, my wonderful students, is called the first excited state. First excited state. And believe it or not, this is actually related to what atoms do and molecules do, and how atoms bind together into molecules. Okay, can you get the next excited state? This one's tougher, the second excited state. It's tough. There you go. There it is. There it is. Look at that. 2 bumps and a dip, oscillating with 2 dips and a bump. Make a sketch of this. This is called the second excited state. And it's not easy to get. All right? These are standing waves. Okay, thanks, you guys. And let's give Kristen a hand. Thanks, Darren. Another thing that I want to show you, did we do this? Did we use these on the first day of class? No? Okay. I want to show you this demonstration of a tuning fork. And this aluminum tuning fork is mounted on a wooden box. One end of the box is closed, and the other end is open. All right? So I'm going to wrap the tuning fork and just listen to the tone. All right. Now, let me do the same thing. These are supposed to be identical. Now listen with your ears and see if you agree that it's the same tone. Sounds pretty much the same? Pretty good. What do you think? Pretty good. Okay. Now, Darian, could you help me with this? Okay, I want you to hold your hand on this. What I'm going to do now is I'm going to strike this tuning fork. Red tie fellas, listen, white shirt boys, frat boys, watch. Okay. All right, we're going to strike this one. And right now, this other one is just kind of sitting there. So I'm going to strike this, and then I'm going to tell Darian to remove her hand and see what effect this one has on that one. All right, now this was tricky. Okay. Hear that? That's the second one. The second one that I never struck. Let's try it again. Let's do it over here by the microphone. Bring it over here. Okay, put your hands on it. Now listen, all right? Take your hand off. Hear that? It's kind of faint. This one was kind of, let's try to do that again. Okay, as soon as I strike mine, I want you to take your hand off. Hear that? That's the second one. All right. That's something called resonance, R-E-S-O-N-A-N-C-E. And believe it or not, that is related to standing waves too. Now, last thing I have to show you is this little, I have a little metal clip up here that I'm going to attach to the top of the tuning fork. And it's going to change the moment of inertia of the tuning fork, the mass, the distribution of mass, and it's going to change the sound of this a little bit. All right? Can you hold your hand on that? Does that sound the same? Let's check it against this one. And can you tell the difference? You can't? Let's try it again. Here, do this one. You hear that wavering sound? Hold that up. Okay. You hear that? Sounds kind of creepy, like a scary monster movie or something. You know, like space aliens come into your backyard. That's called beats. Beats. All right. We're going to talk more about beats today. And that is also related to standing waves as well. So, let's go back to presentation mode and continue our discussion. And we're going to go through some of the basics of wave concepts. And we're heading for the general explanation of the things that you just saw: standing waves, resonance, and beats. Okay, as last time I mentioned that the principal defining feature of a wave is it is not matter moving across space-time, but energy and momentum in a material medium or in a field. For instance, the electromagnetic field. Waves are not easy to localize. You can't say that an electromagnetic wave or an ocean wave is in a certain spot because it has extension and it's in motion. It behaves way differently than a Newtonian particle. So a Newtonian particle, if you want to think about that, think about a cannonball and a musket ball dropped from the top of the Leaning Tower of Pisa by Galileo. Think of a baseball heading for the outfield. That's a pretty good approximation of a true particle. The thing that we've observed on the first day of class is diffraction of hydrogen, helium, and neon. Remember that? First day, and we had the diffraction gratings. Newtonian particles never do that. Wavelets. Diffraction occurs because wavelets are generated at the barriers and at the edges of some kind of a barrier. And I'm going to show you a picture of that right now. This picture shows waves coming in from below towards the top of the picture. And right here, there's a gap. These two dark black bars are barriers that the waves cannot penetrate. But they can go through the gap, and when they go through the gap, all of a sudden, the waves on the other side of the gap are curved. And it's as if every point across the gap is generating not flat waves like are coming in, but spherical outgoing waves. So the wavelets generated in the gap are spherical. And they all add up together to give you this diffraction pattern. So that's an example of wavelet behavior, or the location of wavelets. So in general, waves and particles are like the Hatfields and the McCoys. They do not compute together. Waves do things that particles can never do. Particles can do things or have behaviors that waves can never do. And so you have to have a slightly different approach to handle them. The main equation of motion that we use for waves in its simplest form is simply this: V equals lambda F. Now, let me go up to the next page, and here we go. V equals lambda F. Lambda is the wavelength. That's the symbol for wavelength. Greek lowercase lambda. And that means the spatial distance between two waves. So from peak to peak, or from bump to bump, or dip to dip, trough to trough, that spatial distance is known as the wavelength. The period, capital T, is the temporal interval, the elapsed time. If you're down by the shore, the amount of time from one wave to be followed by the next wave. That's the period. And the frequency in the wave equation, V equals lambda F, is equal to the inverse of the period. So you figure out the period with a stopwatch, and then you go 1 over that, and that's the frequency. It is measured in units called hertz, Hz. So it's spelled like the Hertz Rent-A-Car Company, capital H-E-R-T-Z. It's named after a German scientist who was the first one to actually measure electromagnetic waves in the lab. It was a theory, and then it was measured in the lab by Professor Hertz. And it's symbolized capital HZ, and it simply means so many cycles per second. So if you have a frequency of 10 hertz, that means 10 waves per second going past your point. Okay? Or half of a hertz. That means a half of a wave goes past you. And you got per second. So you got to wait 2 seconds to see the full wave go by. All right? Now, cycles per second, 1 over second. And sometimes in the literature you see the symbol S to the minus 1, meaning seconds to the minus 1 power, or 1 over second. In the wave equation, here's another way to write it. The V is equal to the speed of propagation. Now that's going to be in meters per second for the most part, but for something like sound, sometimes you'll see the speed of sound in miles per hour. That's all right. Wavelength is going to be measured in meters or centimeters, nanometers. Let me think. Electromagnetic radiation in the centimeter and millimeter range, wavelength, is radar. Microwave ovens are in the area of millimeters and centimeters, the wavelength. Frequency, as I mentioned before, cycles per second, or hertz, or maybe kilohertz, K, capital HZ, for 1,000 hertz, megahertz, etc. Your cell phone, I believe, is operating somewhere in the gigahertz, GHZ range. And over in Europe, I think they have a different cell phone system, and it operates at a slightly different frequency band. But those are the specs. That's how you put numbers together in a wave equation. And this is really the equation of motion, and you can think of it as an equation of motion for the wavefronts. And what is a wavefront? Well, the wavefront is like a mental construct. It's or a bookkeeping construct. But you can think of a wavefront as being like you're at the beach and you watch the waves come in. And how do you know the wave's coming? You look at the wave breaking, you know, the crest of the wave. So the crest of the wave all comes on at about the same rate all the way across the beach. That's a wavefront coming in. Then you wait for the next wavefront. But you can easily and equally appropriately say, track the position of the trough between each of those ocean waves. So there's nothing fancy about a wavefront except to note that you can think of this as the equation of motion for the wavefronts. Now this equation of motion, you do not derive it from F equals ma. You know, 1/2 gt squared, yeah, that's the drop distance equation. We get that from F equals ma, but not this one. This one takes a little bit different approach, and we're not going to go into the fancy equations for that. But I'll give you a little indication of it. Now, special kind of wave is light. Light's a wave in the electromagnetic field. Now, this picture here is a picture of water waves in a tank, a glass-bottom tank of water, waves going across the tank, and then this photo is actually a photo of the lab table below the transparent tank, the transparent glass bottom. So you shine a light through the tank, through the glass, and then down onto the lab table and photograph the lab table. The electromagnetic field is the thing that causes compasses to do what they do. In other words, point to magnetic north. And it causes electrons and protons to do their thing, which is bind together to form an atom. Or travel down the wire, if you're an electron, and turn into text or voice or a picture on the internet. The electromagnetic field forms a spectrum, and there's a zillion ways to diagram it. Here's one way. The visible part of the spectrum is here in the middle. It's between ultraviolet and infrared. And the red end of the visible spectrum is right next to the infrared. The violet end of the visible spectrum is right next to ultraviolet. So you can think of ultraviolet as even more purple than the deepest purple that you've ever seen, and infrared as even deeper red than the reddest red that you've ever seen. So the lowest frequency is radio. Wow, this is supposed to be ABC. Sorry, it's starting at the letter C. A little bit higher frequency, infrared. Then the visible. And why do I use the famous physics name Roy G. Biv? We have this mythical physics professor named Roy G. Biv. And it's said in the stories of physics, the annals of physics, that he donated his name to science because the letters of his name, Roy G. Biv, are the exact order of colors in the electromagnetic spectrum. Red, orange, yellow, green, blue, indigo, violet. So go ahead and make a note of that. Roy G. I don't know why Roy G. Biv is easier to remember, but then above the Roy G. Biv visible band is ultraviolet, and that's the thing that gives you sunburn. X-rays, these are the ones that take pictures of your bones, because X-rays do not penetrate your bones very well. They do penetrate everything else fairly well. And the speed of light, it's a constant of nature. 3 times 10 to the 8 meters per second. That's 300 million meters per second. That's really fast. 186,000 miles per second. Very, very fast. We're about 500 light seconds from the sun. All right, so it takes, that's how far we are away from the sun. You know, you've heard the term light years. Well, that's the distance that light travels in 1 year. A light second is the distance it travels in 1 second. 3 times 10 to the 8 meters. And we're about 500 of those light seconds from Earth. By the way, up in item number 2, make a side note up there, or a star or something, between radio and infrared. Sometimes you'll see the term microwave also lumped together with infrared. Some people might call a certain frequency infrared, and another kind of engineer might refer to it as microwave. Microwave is a communication, and in your kitchen is the frequency that drives your microwave oven. So similarly, between ultraviolet and the X-ray, some people might call a high-frequency ultraviolet a soft X-ray. So there's no hard and fast boundary, except for visible, and I'll probably give that to you next time. Now, here's a question that we've got to work out and study, and that is, why do any physical systems oscillate? The simplest example of an oscillating system is just a spring, like this coil spring. All right. The force law is, you know, you take a spring and it takes some force, some newtons to stretch it, and some newtons to compress it. All right. And that distance of compression, the amount of squeeze down, the amount of stretch out that you do with like 1 newton of force, that is a property of the spring itself. It's called the spring constant. So the force for a true spring is proportional to the distance x. In other words, the more you displace it, the more you stretch it, or the more you compress it, the more push or pull that you get from the spring. So when you compress it, it's trying to press back outwards. If you stretch it, it's trying to pull back inward, and that's the next feature. The force is a restoring force. It's trying to get back to equilibrium. So whatever direction your displacement is, the force is the opposite direction. Now, I'm going to give you a diagram here. See if you can sketch this diagram. The upper part here shows a tabletop with a reddish square object, and it's connected to a spring. And we're going to say that this position, x subscript 0, is the equilibrium position. So in the upper picture, the red square object is centered at x subscript 0. And what that means is it's not getting any push or any pull from the spring. It's just kind of sitting there. Now, in the second diagram, we've pulled it over to the right. And if you think about what the spring will do, the spring will pull it back towards the left. All right, back towards equilibrium. All right, so Roman numeral I. If the position is right, of equilibrium, the force is leftward. And that's the diagram that we have. All right. Now, I don't have a second diagram, but we can, let's label this one up. All right. So in the upper diagram, there's no push or pull because it is located at the equilibrium point, or the center of mass is located at the equilibrium point. In the second diagram down here, the equilibrium is out here at position X, or excuse me, the red object is out at position X, and so you have a leftward pull force. So go ahead and make a leftward pointing arrow, and you could compute the number of newtons if you needed to. You know, every spring is rated, 15 newtons per centimeter of stretch, either compression or stretch, or 25 newtons per centimeter, or a car spring is going to be, like many thousands of newtons per centimeter of compression. Now, I didn't draw it in, but you can do what you think is good. If the position of the red square object is to the left of equilibrium, then the force will be pushing to the right. In this second diagram, it's pulling to the left. But if you compress it, if you go left of equilibrium, you get a push force. The push force is back to the right. And so for a spring, if you think about it, it's either at equilibrium or it's being pushed towards equilibrium or pulled toward equilibrium. So the equilibrium point is the symmetry point in terms of the forces. The force law is simply this: F equals minus kx. And I'll make a side note for you that the minus sign indicates the direction, that it's restoring. So if x is positive, the newtons are negative. Negative newtons means to the left. X is positive means position is to the right. Position to the right means you've stretched the spring. So the spring is going to pull you to the left, negative newtons. Similarly, if your position is left, that means x equals like minus 5 centimeters or something like that. You're going to get a push to the right. So your newtons have to be positive. And this minus sign handles that. The potential energy function, the spring potential energy, SPE, slightly different form, 1/2 kx squared. Oh, and by the way, students, K is known as the spring constant. I don't think I have it on the slide. Go ahead and make a side note somewhere. K is the spring constant. And K encodes how easy it is to stretch or compress the spring, or how hard. So you might have a spring constant, K equals 100 newtons per centimeter. Or you might have a spring constant, K equals 5,000 newtons per centimeter. That would be a stiffer spring. Right? So the spring constant, a big spring constant means a very stiff spring, like a car, like the coil inside a car suspension. But if you think of anything else, what else has springs in it? You know what has springs in it? The turn signal. The turn signal is flipped back up to its neutral position after you make your turn by a little spring. Okay, now that spring is going to be very small spring constant. Now here's wisdom. Anytime that we see a spring force, a restoring force, minus K, so a negative sign, and then a constant, and then a coordinate, whether it's X, Y, or Z, or R for radial motion, or any other coordinate, we know that we have a restoring force. We have a force that will oscillate about the equilibrium. So make a note of that. It will oscillate. It will oscillate about the equilibrium position, wherever that happens to be. Similarly, anytime if you're working in terms of energy and not forces, and you work out that you've got a factor of 1/2 and a constant of some kind, and the square of a coordinate, like x squared, yep, that tells you in terms of energy that you're going to have an oscillatory system. All right, let's keep going. Oscillating systems. What does one full cycle mean? Well, in a spring system, and try to make a sketch of this spring system on the right. The upper diagram has the spring, this kind of square block object, positioned at equilibrium. And then it's out at maximum extension, and it comes back to equilibrium. So there are 4 journeys to or from equilibrium for one full cycle of a spring system. All right? So here's the first journey, from equilibrium out to maximum extension. Right? Now, maximum extension is where the block is located in the second diagram down. Okay, so I drew a dotted line to indicate that this object will go a certain distance and no further, and then it'll turn around. And once it turns around at maximum extension, the turning point of the motion, yep, it starts going back. It's going to slow down and turn around and then start going back towards the equilibrium. But of course, it's going to overshoot the equilibrium because it's going to be in motion when it gets to the equilibrium. So here's the equilibrium point again. In the third, my dotted line indicates that from max extension, you get back to equilibrium after a short interval of time. But you keep going. And whoops, you keep going out to the left. And at that point, let me drop down the third line segment, the third dashed line. Now you've got max compression. So this could be like -2 centimeters. And max extension to the right would be +2 centimeters. And then equilibrium would be 0.0 centimeters, for instance. Okay, so when I say, and then here's the return to equilibrium. Okay, so 4 journeys, 4 line segments, all the same size. They're just different directions. All right, and there's one full cycle of the motion of a simple spring system, an oscillating system. Now add those all up and you get one full vibration, one full cycle. Now, all this is to introduce to you a term called amplitude that lazy mathematicians and scientists that know a lot of trig and calculus decided to use instead of the full distance from max compression to max extension. They decided, let's just use the arrows that show from equilibrium out to max extension, or equilibrium out to max compression. Right? And that's called the amplitude of the wave or the amplitude of the oscillation. And the reason that they do that is because of for those of you that have had calculus, the derivatives of the trig functions sine and cosine make this extremely nice. If you haven't had calculus, forget about what I just said. But if you have had calculus, you know it comes out from that. Anyways, it's still a term that we can think of, and it's not a bad one to think of. Think of a wave out in the ocean. All right? And go ahead and draw a squiggly wave here, a few cycles of the wave, a few wavelengths worth. And right through the middle, let's draw the equilibrium or sea level on a calm day. All right? And what a wave does is it'll have a tall crest and it'll have a deep trough, and then it'll go to a tall crest, and then another deep trough, and they can get pretty big. This is the amplitude, the height of the crest above sea level, or this, the depth of the trough below sea level. Either way you look at it, it's half of the full distance from tippy top to the very bottom. Right? Half the distance from max compression to max extension. Half of your full variation. All right, so that's a diagram in terms of ocean waves. The electromagnetic field, the really cool thing about it is that the power, or the energy per second, is proportional to the square of the amplitude. And very fundamental result. All of the Big Bang theory uses this particular cool feature of the electromagnetic field to figure out what's happening during the first few seconds of the universe. Okay, let's work on the electromagnetic wave equation. Looks just like the generic one. And this one has, instead of generic V, for the speed of light we use the symbol c, which I've mentioned. Now, in this one, lambda is, as before, spatial dimension, the wavelength. So centimeters, meters, kilometers, whatever you want, nanometers. Period is temporal, seconds, milliseconds, nanoseconds, etc., etc. And the frequency is 1 over the period, so hertz, megahertz, gigahertz, capital G, capital HZ, or terahertz, capital T, capital HZ. And we're going to calculate something in terahertz. Make a side note to yourself. Capital T, capital HZ, terahertz, that is the same as 10 to the 12th power cycles per second. 10 to the 12 cycles per second. 10 to the 12 hertz. So instead of writing 10 to the 12 everywhere, you can just write capital T. And gigahertz is 1 billion cycles per second. So 10 to the 9. So if you don't want to go around writing a bunch of zeros or 10 to the 9, you just write in capital G for gigahertz. All right. Now we're going to calculate a frequency now for a red color. And the wavelength that I have chosen is 656. 656 nanometers. All right, now if you haven't studied that part of the book, the appendix, a nanometer is a billionth of a meter. 10 to the minus ninth of a meter. The billionth part of a meter. And we'll use that in a second. Now, to do this, to figure out the frequency, which we're going to do, we take the wave equation and we just modify it a little bit. We drop the lambda over to the left side and leave f by itself. And so this now, what we're going to do now is divide the speed of light by the lambda, by the wavelength, 656 nanometers. Now, if you have the frequency and you want to find the wavelength, you just use this. You know, you make a side note. We're not going to use this one, but you might use it on homework. This one will help you find out the wavelength. All right? So here we go. C over lambda equals F. All right? The numerator here is C, 3 times 10 to the 8 meters per second. And the denominator is 656 times 10 to the minus 9 meters. Now, I told you that that's 656 nanometers. All right? It's written across the top as nanometers. And in the denominator of this first equation, it's 656 times 10 to the minus 9 meters. All right? Now, that's my calculation for F. Now, you can rewrite that in this way. It may seem a little simpler to you. And this is the way that you'd have to handle it if you're doing it, if you don't have your calculator. If you have your calculator, you can just type it in. But if you don't have your calculator, you've got to do it on paper. It's not too bodacious. The numeric part, 3 and 656, they just form a simple fraction. Now, 10 to the 17, where does that come from? And where does that per second come from? Well, the per second is pretty easy to see. The meters in the numerator, that's the speed of light, cancels the meters in the denominator for the wavelength. But it leaves per seconds up here in the top. All right, and that's what I've got over here in the far right. 10 to the 17, the reason that that is true is because when you have 10 to the minus 9 in the denominator, you may remember this from algebra class, 10 to the minus 9 in the denominator is the same as 10 to the regular 9 or 10 to the positive 9 in the numerator. So the numerator could be expressed as 10 to the 8th times 10 to the 9. Right? 10 to the 8th times 10 to the 9, that's 10 to the 17. All right? Questions about that? Yes?
Is 10 to the negative 9 how you get from meters to regular meters?
Yeah, a nanometer, this little n up here in the very top, that stands for nano. You can replace that with 10 to the minus 9. All right? And then the 10 to the minus 9 goes, you could flip that up to the top. Yeah. Question?
How did you get this? Like, where's the 3 from?
The 3?
Yeah.
This 3?
Yeah.
Speed of light. 3 times 10 to the 8 meters per second. Now, if Albert Einstein were in the lecture hall, he'd say, "My dear, what," but he'd say, he'd be pretty cool about it. But anyways, yeah, speed of light. All right, now, if you're typing this in on a calculator, you could type it in like this. 3, and then the EE button, if you have a TI calculator, and then a 17, and then divide by button, and then 656. All right? Go ahead and try it. Get your calculator, and you guys, you're going to need to know how to do scientific notation on your calculator. Your iPhone has a fairly nice scientific notation feature. It has the EE button, TI, but if you have something like a Casio or Hewlett Packard, I think it's got a different button, but you'll have scientific notation, and you've got to figure it out. I won't be able to help you on the exam. You've got to figure it out in the next week or two. And when you do, you'll come to this result. It'll be 4.57, and it'll have a little 14 up in the upper right on your calculator. And that means 4.57 times 10 to the 14 per seconds is. Now, a per second is the same as a hertz. And so this one is 457 terahertz. And so if I were to ask you this on homework, I'd ask you, how many terahertz? And you'd write in 457. Now, you may be saying to yourself, Dr. B, what is this business with terahertz? I thought it was 10 to the 14 hertzes. All right. 4.57 times 10 to the 14, that's the same as 4.57 times 10 to the 2 times 10 to the 12. All right? 10 to the 14 is the same as 10 to the 2 times 10 to the 12. All right? Now, you keep the 10 to the 12 because that's tera. That's the capital T. And you multiply 10 to the 2 times 4.57. Hey, what's 10 to the second power? It's 100. All right? So 100 times 4.57 is 457. So keep that and the 10 to the 12th, and there's your terahertz. Ching. And you'll have some practice with wavelengths and stuff in homework 12. Let me pause for a question. Yes.
Why are you taking it out of scientific notation?
Why am I?
Taking it out of scientific notation.
Because I'm taking it out of scientific notation because sometimes students they forget their calculator on exams, or they don't bring it to class. But if you have what is your first name again? Morgan. Morgan, if you have a calculator and you know how to use scientific notation, good. All right. This is if you forget it. It's not. It's really to show you that it's not too bodacious on paper. If you do forget your calculator, you're not sunk. All right. Now, IQ test on the iClicker. I want you to look back to the standing wave demonstration, and I want you to think about the fundamental mode. Did you write a sketch of the fundamental mode? It looks something like this. Yeah, so this is a half wavelength. All right. And I'm sorry, I thought iClicker was working again. Very frustrating. All right, let's talk about the concept of interference. Now, this is the heart of our lesson, so be very careful with your notes. The interference of waves is behind many interesting effects, like the standing wave that we saw, that Darian and Kristen demonstrated, the tuning fork demonstration of resonance, and the tuning fork demonstration of beats. So basically what you do is you start with two sources of waves. So that's Kristen and Darian. All right. That's the two tuning forks. The waves move out independently from the two sources. And if you're thinking about the ocean, it could be a storm off the coast of West Africa and a storm off the coast of Nova Scotia. And somewhere in the middle, the waves from both of those are going to interact. At certain points in the ocean or in the classroom, if you're listening to the sound waves, you might have two wave crests meeting, and that'll give you a super big surf or a rogue wave, as they call it. If you get at some other point two troughs, so half a wavelength away, you might get two troughs meeting. Well, that's fine. You get an extra deep trough in the ocean. Those two effects are known as constructive interference. The two waves interact, and for that instant of time, you get more wave. You get more amplitude above sea level, more amplitude below sea level for that instant of time at that location. Now, at some other point in time, you might get a crest and a trough that interact. All right, if that's the case, you have no wave for that instant of time at that location. And that, my wonderful students, is known as destructive interference. It's flat water. Right? So constructive and destructive interference, when you look through those diffraction gratings, you are observing the effects of constructive and destructive interference in one glance. Now, here's a set of diagrams I want to go through with you. Here are two ocean waves, for instance. Wave A heading to the right, wave B heading to the left. And they're both about the same shape. And when they interact, they add together, and you get a really big wave. The technical term here is the two waves are in phase at this point, at this moment of time. They might not be in phase everywhere, but at this point, at this time, yes. And then after that, so this is the rogue wave out in the ocean. All right? So now the rogue wave's at the top of the screen. after they interact like that, they keep going. Wave B keeps, heading off to the left. Wave A keeps heading off to the right. Right? That's what waves do. It is the propagation of energy and momentum. So the water molecules are just kind of participating. But the water molecules aren't heading off to Nova Scotia, at least not that fast. There might be an ocean current heading that way, but. Now, here are two waves, and one of them is a dip, and one of them is a trough. So this is a different set. And here they are approaching each other. And down here at the bottom of the screen, where they interact, A plus B, flat water, zero amplitude. But only for this point in time at this geometric location in space. And the fancy term for that is 180 degrees out of phase, or just out of phase. It's like facing two different, 180 degrees, one person's facing forward, the other person's facing backwards. Okay, out of phase. And then what? These guys, they don't get destroyed. It's interference, but you don't destroy the wave. The only way to destroy the wave is to go crashing into the beach. And wave B keeps cooking off here to the left, and wave A keeps cooking off here to the right. No problem. That is what waves do. And as a side note, this is a two-dimensional wave picture. Now, it's a one-dimensional wave picture. In the ocean, waves are three-dimensional, really. Actually, you should say they're four-dimensional. Another interference effect, and that's the concept of beats that we listened to already. Now, here's a diagram from a textbook that shows beats, and it works when you have two sources of slightly different frequency. Now, when I put that little metal clip on the first tuning fork, it was a little bit off tune. It was a little bit out of tune. All right, and we got beats. Now, here's a much nicer picture. And I did this myself. So let's take a look. Two waves, slightly different frequencies. The beat frequency, F subscript B, is simply the bigger frequency minus the smaller frequency, whatever that works out to be. All right, so think of it as sea level waves or sound waves. Here's the equilibrium lines, okay, right through the middle. The top wave and the second wave. The top wave's in black, the second wave's in red. And I just did the simulation here with a propagation speed of 80 meters per second. That's pretty fast for an ocean wave, but it's a nice round number. And so let me park that up here to the upper right. And I set up the frequencies to be pretty close together. So frequency F1 is 106.7 hertz. And I set up frequency 2 to be 119.5 hertz. So they're both just above 100, but they're not. So you would know the difference. You'd be able to hear the difference. You'd be able to hear that and know that they're slightly off beat or slightly off tune. Now, those two waves combine at your eardrum, and this is what you would hear. You would hear the sum of those two. So try to draw kind of a squiggly one that starts out high amplitude over here and then goes to low amplitude right about here in the middle. And on a computer, you can do this exactly, which is what I did here for this diagram. And then it goes back to high amplitude over here to the right. This is what you would hear. All right? You know, both of those sounds combine at your eardrum, and you would hear beats, as we did just a few minutes ago at the beginning of class. High amplitude. Right here, that's where it's loud. Here, low amplitude, almost zero, it's very faint. And then over here again, high amplitude again, because of destructive interference and constructive interference, we get loud noise. And so that's the beating sound, from loud to faint, from loud to faint, loud to faint, loud to faint. The beat frequency in this example, 12.8 hertz. That's just the difference of the two frequencies. Okay, at 80 meters per second, the lambdas are particularly easy. That's why I set it up this way. 0.75 meters for wave 1 on top, 0.67 meters for wave 2 in the middle. And then the beat frequency works out to, the beat wavelength, 6.25 meters. That's this distance. Draw this in on your sketch. That is the beat wavelength. Beat frequency is just the difference between the two frequencies. And if you mapped it out with a computer and stuff, this would be the beat wavelength. Much longer. Large wavelength, small frequency. All right. All right, next time I'll show you how cops use beats to nab speeders. You're dismissed. Homework 12 will start in 5 minutes.